Okay. Now, what we're going to do is that we are going to uh, understand how does the heap sort works. Now, till now, what you know is that we are going to make a heap tree first, and then after that we have to perform the heap sort. Now, what we do is the heap sort. Now, what we can start with, we are already having a heap tree, and the heap tree will be something like this. Let us take a max heap like this. Okay. Now this is a heap tree. It's very clear because the root is the maximum, then all its children, and therefore this definition holds at all level. Now, this you already know that the height of the heap tree will always be the maximum of log n. N is the number of nodes. Therefore, when we are going to add a node, you always have to add in such a way that it becomes a binary search tree. Now, what we intend to do is the sorting step. Now, how to do the sorting step? What we have to do is that we have to let us see how to apply the sorting. Now, how to apply the sorting? Let us see. What we do is that we remove the root. We are going to remove the root. When we are going to remove the root, we'll maintain this in some place. Therefore, what we are going to do, we are going to maintain the array like. We are going to maintain, and that means remove the root. We are going to maintain like this. And when I remove the root, I have to find a new root. Now, the process is simple. When I am going to find a new root, what I do is that I replace with the last element. Now, the last element means when you are having an array, the last element is the last element in that array. And you know it very well. When I am having an array, it contains 100, 80, 70, 60, 20, 15, 65, and 30 is the last element. Therefore, what we are going to do, we are replacing this by 30. And at that time, we are deleting this 30. We are deleting 30 over there, and that means what we have to do is that replace last number, a node, at the root. That means you replaced the last number at the root. But you know that when I do this, it's a binary search tree, but it is not a heap. It is not a heap. Why? Because the root is smaller than its children. Now what we have to do is that we have to now sync the node. Therefore, now what we have to do is that we have to sync the root to its position. That means we'll sync the root to its position. Now, what is the meaning of position? You have to sync it such that it remains a heap. Now, what you have to do is that, now in this case, we will compare 30 with 80 and 70 both. And the bigger of them will not be replaced by that number. That means I will compare 30 with 80 as well as 70, and I will replace 30 with the node which is bigger than the with the left or the right. Now here I will compare this one. I will compare this with this also, and I will also compare this with this. And I find that 30 is bigger. It is bigger. Then what I am going to do, I will be going to replace this one with, say, I will replace this with this, and 80 will come here. Now I again check whether it's a heap. I find that this is not a heap. Why? Because 30 is at the root, and 60 and 20 is at the as a child. Therefore, again you are going to again compare this with this two, and you find that 60 is bigger. Therefore, what you are going to do is that you are going to replace this one with 60. And you are going to replace this 60, and now you find, now this is the heap tree. This is the heap tree. Now this is the sorting step. That means it is going to sort this. Now when you are going to perform this sorting, how much time you require to that to be synced? How much time? Yeah, how many steps you require to be synced?
So log in, no?
You require login times, because in the maximum, in the worst case, the node will sync from the root to the leaf. In the worst case, it will go to the leaf. Now, when I am going to perform this, that means it is going to take a login times. Now, again, what you do is that again you do the same thing. You are going to delete 80 and store over here. Now, when you are going to delete 80, you are going to remove the 65, and then you are going to put 65 over here. And then you compare 65 with left and right both, and what you are going to do is that when you are going to do, when I am going to do with this, you know that 70 is bigger. Therefore, what I will do, I will just remove this 60, this one, and put 70 over here. Sorry.
Sir, why not this time we remove 30?
If you remove 30, it will not become a binary search tree. Sorry, it will.
Sir, then we again replace the last node, and then we can again sync the root.
Sorry, it will not be a complete binary tree, because in a complete binary tree, the nodes must be pushed to the maximum left. Therefore, you have to only remove the. Now you have to remember that what I am trying to do, I am maintaining an array for this. No.
Yes, sir. Yes, sir.
Therefore, the last element what is there, you have to replace over there. Now, in that case, this is 70, this is 65, 60, 65, 30, then 20, then 15, like this. Okay. And at this moment, you have to make sure that you remove the. Now again, that means when you are going to sync the root to its position, it will take a maximum of height. It will take maximum height, and you know that the maximum height is equal to log n. That means for each element to sync to its required position, it will require a log n times, and we are going to do it for n number of nodes. Therefore, it is equal to n into log n times. Now that's the worst case. That means if you are going to now here, if you see this example, when I sank 65, 65 did not come to the root. It only moved one position. But in the worst case, it might move to the last, that is at the leaf, and therefore the maximum of this is nothing but you know it is log n. And you keep on doing a number of times, and you will be finding that all these elements will be sorted in descending order. Now that must clear a doubt that when I am going to perform the concept of descending order sorting, I will make a max heap tree. I'll perform a max heap tree. If I am going to perform in ascending order, I will use a min heap tree. That means now this should be very clear to you that when I am going to build a, now in that means there are basically heap sort requires different steps. First of all, you are going to make a heap. Then you are going to heapify at that moment. And then the sorting step where you are going to delete the root. Now how much time deletion of root will take place? Order of 1. How much time replacement of last element to the top will take place? Order of 1. How much time it will take in order to move the node from the root to the leaf? Obviously log n times. Therefore, actually one step takes order of 1 plus order of 1 plus order of log n. Okay, that means it is basically order of 1 plus order of 1 plus order of log n. Now what is the order of 1? It is to delete the root. What is order of 1? Let me replace last element as the root. And this is sync the root to its actual position. And if you take this is nothing but order of log n. This you are required to do for one node. And therefore, since this step is repeated n times for n node, therefore heap sort step will take n log n times. This is only for one node. And when you are going to repeat it n times, this will be n into log n. Now this is the worst case complexity. Obviously, you must think that log n times n is maximum, but every time you are going to decrease n. But when you are going to decrease n also, you are going to, this n is actually will keep on decreasing. Because once, if n is suppose 7, the height is 3. When n will remain as say 3, height will only become 2. Therefore, actually, this value of n will keep on decreasing, and this n will not be constant for the whole thing. But when I talk about worst case, it is nothing but when you are going to take the things as for all number of nodes in that. Okay. Concept of that means when you are going to do this, it is basically as an in-place sorting algorithm. And now, what is the space complexity required? What is the space complexity of the algorithm? How much space it requires? Extra space.
So omega of 1, constant space.
Order of?
No, actually, sir, 1.
1. Order of 1. That means just require 1 for swapping. Okay. Now it means that to just sum up the things, we build a max heap tree from an unordered array. Then we find the maximum element which is located at the top. That means the root, because we are going to use the max heap. Then we are going to swap the AN with A1. Now this swapping step is nothing but replacing AN with A1. Then in that case, when we are going to move that, of course the size of the heap will now become one less. And then we are going to make this is called as the syncing is called as the max hippify function. That means what you are going to do, you are going to do a max hippify. You are going to do a max hippify. Why is it max hippify? Because you want the tree to be max heap tree. Okay. Therefore, in that case, we are going to do it max. Now, one thing what you should remember, when I am going to delete the last node, the other nodes are already heap. That means when I am going to delete the last node, for example, if I delete 15 also over here, now the node, other nodes will automatically be heap. There is nothing to do. That means this is already a heap. Now this is already a heap. Okay, that means the only difference what will happen will be when you are going to replace that, the other nodes will always remain a heap. Okay, and this is now the algorithm is very simple. What you will do is that you are going to first you are going to build a heap. You are going to put at 2 into I and 2 into I plus 1. Then you are going to compare the left with the heap size. That means you find the largest one of them. Now you have to keep on thinking that what we are trying to do, we are only trying to do in an array. Therefore, nothing we are trying to do in a tree. And therefore, when I am going to use this concept, what you are doing when you are comparing that, syncing it, you are going to check with the child, and child you know is already at 2 into I and 2 into I plus 1. Okay. Correct? Any questions?
Sir, one thing, sir. Sir, like in the heap sort algorithm, sir, the time complexity is omega of 2 log n. If you will see for the creations of heap and for the deletion, it will take totally it will be 2 log 2 base n. No, but sir, if we will take sir only log 2n, order of log 2n. Why? I don't know why it's we take.
See, actually, to build a heap, you require an order of n log n, isn't it? See, there are 2 steps for this. First of all, you are going to build heap. Then you are going to, in the build heap, you will have to have a heapify. Then you have a sorting algorithm. That means heap sort requires first to build a heap tree. For a build a heap tree, you require 2 steps. One step is that you are going to insert the number, and then you are going to make sure that that number is at its correct position, and that requires you to perform a heapify. And that already told you yesterday that will take an order of n log n. Now the sorting will come after you already get a heap tree, and once you are getting a heap tree, you have to perform these three steps, which will again take an order of n log n. Therefore, completely it will take an order of n log n plus order of n log n, because those 2 are independent steps. They are not nested. Therefore, it will take order of n log n for the build heap and the heapify. Then the sorting will again take order of n log n. Therefore, it will take order of n log n plus n log n. We will give you order of 2n log n. But here, it is not that 2n log n is the worst case in a strict sense. Why? Because when we talk about this, we take log n is equal to the height is log n. But log n height will be only when you are having n nodes. Every time when you are decreasing the number of nodes, the height of the heap tree will be less than order of log n. Therefore, when you talk about the worst case, it is order of 2n log n. But that worst case actually will not come, because that will only come. It will never come, because we are taking that we are syncing the node at the log n position, where n is the number of nodes which are initially there in the heap tree. But every time when you delete a node, the n keeps on decreasing by 1, and that means at the time will come when you will have, suppose I am having this one. Okay, let us take this step. There are 7 nodes. The first step you will have of log of 7. Maximum you can take. The second step, obviously, it will again have a log of 7. Third step will also have again log of 7. Sorry, log of 6, log of 5. Then you will have log of 4. But in that case, the next step, you will have only log of 3. Because now this all will go. After 4 deletion, this will go. And you will have only, you have to only sing one time. Now log of 3 will be nothing but, it will be only 1 only. That means it will be log of 2 power 1. That means in that case, it is something like this. That will do something equal to approximately 1. It means that you require only one comparison. You require, because whatever number you will get, suppose I get 50 over here, and this is say 60 and this is say 70, you just require one swapping, and this will go to become 70 and this will become 50. That means you require just one comparison. Okay. But when I am talking about the general case, what I am trying to do, I am doing n number of nodes multiplied by log n times to sync. N number of nodes, and each node requires log n time to sync. Actually, this n here is equal to 7 in this case. But actually, log n is not 7 every time. One time it is 7, then you have only 6 nodes, then 5 nodes, then 4 nodes, then 3 nodes, then 2 nodes. And when you have a single node, it does not require any syncing. Okay. But one thing is clear, you have to understand that if this tree is something like this, then you are having 4 nodes, but you require how many times to sync? 2 times. Therefore, this is nothing but this is nothing but equal to log of 2 square, which is equal to 2. That means you require one time over here. You compare one with this and one with this. That means one time and 2 times. If you go in this way, otherwise, if it comes to this side, it will be only one time.
Yes, sir. Sir, that means sir, it's we take the 2 n log n जो होता है सर वो मतलब पोस्ट केस होता है नहीं, but in actual it yeah upper bound yes simply upper bound.
upper bound, but वो वर्स्ट केस आता नहीं है कभी. वो कभी वर्स्ट केस आएगा नहीं. इसलिए नहीं आएगा कि वो तो हम इसलिए जोड़ रहे हैं कि अगर हमारा मानने के एवरी टाइम जो हमारा हाइट है वो लॉग एन टाइम्स है, बट लॉग एन टाइम हमेशा होता नहीं है, वो हमेशा घटते आता है. जब हम उसको सीख करते हैं तो लॉग एन टाइम हम आते हैं, बिकॉज ट्री का जो साइज है वो हर स्टेप के बाद कम होते जा रहा है. ओके, देयरफॉर though it is an order of n log n, 2n भी बोल सकते हो in the worst case, but ऐसे होता है ना, कुछ एल्गोरिथम ऐसे होते हैं जिसका वर्स्ट केस होता तो कुछ बोल सकता है, बट वो वर्स्ट केस कभी आता नहीं है. It will not be because, but when you talk about a general case, therefore हम इसलिए मानते हैं कि n अगर बहुत बड़ा है, then it might be like this. ठीक है. इसका वो आसान है काफी. The algorithm is very easy. Just you have to write the algorithm. इसका एक और है कि इसमें एवरेज केस, वर्स्ट केस और सारा केस जो है ऑर्डर ऑफ n log n ही होता है. Order of n log n. Why? Because every time you have to perform a syncing. Worst case का बेस्ट केस भी वही होगा, बिकॉज तुमको जो लास्ट नोड उसको रिप्लेस करना होगा, सिंक करना ही पड़ेगा. तो ऐसा कुछ में नहीं है कि अगर तुम्हें कोई भी होगा इसका ऑल केसेस विल बिकम इक्वल टू n log n. तो अगर तुम क्विक सॉर्ट देखोगे, क्विक सॉर्ट का वर्स्ट केस है तुम्हारा n स्क्वायर, बट इसका जो है n log n ही होता है हमेशा. जितने भी एल्गोरिथम देखेंगे हम लोग, सारे एल्गोरिथम तो हम लोग इस कोर्स में नहीं पढ़ने वाले हैं. तो जो भी पढ़ेंगे वी विल फाइंड दैट n log n एल्गोरिथम बहुत नहीं है. कुछ ही algorithms n log n में है, and therefore this is a good algorithm as far as this is concerned. Okay. Now let us try to see any questions which are there. ये आसान है, तुम इसकी प्रैक्टिस करना. I'll just give you some questions from the book. Now, if you see the book, there are few questions given, but those are simple questions, not too simple that you are given some numbers and you have to create a heap tree out of that. Now, it could be like this. That means question might be like this: that create a heap tree from something like this. Time complexity of order of any constant times n. Okay, what you're trying to ask is that shall we take order of 1 into n times? You see, we might ignore because of the fact that if it is constant times and it is going to do n times, therefore it is basically, if you ignore order of 1, it is ignored or not. होता क्या है कि जब तुम ऑर्डर ऑफ n log n प्लस समथिंग प्लस समथिंग प्लस समथिंग लेते हो जिससे छोटा होता है, दैट डजंट मेक्स एनी डिफरेंस ओवरऑल. जैसे कि मान लो हमने ये लिया, मान लो ये आया किसी की, ये तो कांस्टेंट है, तुमने इसको हटा दिया, तुमने ये तो कांस्टेंट है, तुमने इसको हटा दिया. अब ये बड़ा है, ये भी छोटा है, इसको हटा दिया, ये भी छोटा, इसको हटा दिया, तो एक्चुअली ये log n ही हो जाएगा. बट व्हेन यू आर रिमूविंग इट, अगर मान लो कहीं पे यहाँ पे ऑर्डर ऑफ इसके बदले होता ऑर्डर ऑफ से 10n, ऐसा होता, तो शुड नॉट इग्नोर दिस बिकॉज n is also a big value. Therefore, it is not to be ignored over there. Therefore, अगर कोई एल्गोरिथम है ऑर्डर ऑफ 1000n, इसके मतलब नहीं कि तुम 1000 हटा दो, because 1000 is big number. You cannot directly ignore 1000n.
Sir,
Yeah.
excuse me. Sir, who just describes the rate of increase of any algorithm. So why will we take the constant? I mean, it's the rate of increase.
Okay, that we will discuss in the, that is the unit 1 is already there. वो अभी हमने पढ़ा, इसमें एक क्वेश्चन छोड़ा हुआ है. Asymptotic notation जब पढ़ाएंगे उसे बताएंगे कि what is the use of rate of increase of an algorithm, कैसे calculation करते हैं. If you just give me 1 day to finish this chapter, and then we'll come back to the first unit where asymptotic notations, जैसे ये बताया था, अभी omega notations, अभी हम omega के बारे में बात नहीं कर रहे हैं because I have not taught you. You might have learned from the book, but I am talking about only from the order of the BIGO. Reform BIGO करते हैं. But I just clear your doubts. Now, two topics remains to be done. One is a Hoffman tree, we'll discuss, and then second is a B tree. B tree. Now B tree तो मैं database से पढ़ाया जाएगा आगे जाके, but चूंकि data structure में हम लोग tree कर ही रहे हैं, therefore I'll just try to do the B tree. Okay. Okay, now stop at this point because I have another class right now at 1 o'clock. If we will see any questions you want to ask, you can ask. ये किताब में से तुम चाहो तो you are going to use this book for practicing some questions from there.
What is the name of the book?